We're now going to go over this extra problem, 1B, the shortest path to your heart, run a star search, starting at A, going to G. And so before we even jump into this problem, let's just remember the high level differences between A star and Dijkstra's. We are starting at A and we have a specific goal in mind, G, and we have these heuristics given in parentheses that help us estimate how far a given node is from our goal G. And so when we say, for example, this parentheses 3 above the C, that's just letting us know we estimate that C is 3 distance away from G. Similarly here, we estimate that E is 3 distance away from G. Our estimate isn't always perfect. That's the whole reason we call it an estimate or a heuristic. For example, we underestimated here, but that's okay, as long as our heuristic is admissible and consistent, which means that it's not overestimating the costs, basically, and it's being, I guess, consistent, right, between estimates it's given here. And so this is A star search. We're just going to run it starting at A. And you're going to notice that our priorities in the priority queue are the sum of the distance to that edge, or the known, what we know so far, as well as our estimated distance to the goal, right? So A starts us off in the priority queue with a priority of 7 because we estimate that it's 7 away from the goal. And we're starting at A, which is why we just put that in there, and it's sort of our kickstart or activation energy. And so we put in the queue and then we pop off the queue, right, as always. And so we pop A off the queue, and we've now confirmed the distance to A is 0, and there's no edge to because that's our starting point. And we're going to go ahead and look at all the children. So first we're going to look at B, right? And I want you to take a moment and think, when we add B, we're going to have to add it to the queue as well as update our distance twos and edge twos. So take a moment and think about what those might be. Well, the distance to B is going to be 1, right? Because we know if we're at A and we traverse this edge from A to B, the total cumulative distance from the start, or A, to B would be 1. That's our distance 2. And our edge 2 is A because we traverse this edge from A to B. Our priority in the queue is 7 because we know that the total distance to get to B is 1, and we're estimating that from B, we're still going to be 6 away from the goal. And so we're basically saying B is in the queue with priority 7 because we estimate the total path from A to G, if we were to go through B, is going to be roughly 7. That's our estimate. We're saying from A to B, as well as from B to the rest of the goal, right? And so that's why it goes into the queue with priority 7. Next, we're going to look at the next child, E. And so we see that if we were to traverse E, it would have a total distance of 7 from the start to E, right? And our edge 2 would be A if we traverse this edge. And our priority in the queue is going to be 10 because we say that it's the distance 2, which is 7, plus our estimated heuristic from E to the goal, which is 3. And that gives us 10. And so what we're saying is we estimate, not only do we know it takes 7 to get to E, we're going to guess that it takes still like 3 more to get to the goal from E, right? And that would lead to a total path from A to E, and then from E all the way to the rest of the goal of 10. And so this goes into the queue with a worse priority than B, because our total priority here is representing that the path from A to G, if we were to go through E, is going to be probably around 10 distance, right? And that's worse than a path that's of distance 7. And so E goes into the queue with that priority. In other words, our heuristic is telling us, like, once you get to E, you still have to go 3 more, right? And next, we're going to look at A's child, D. And so the distance to get from D, to get to D starting at A would be 2. So that's our distance 2. The edge 2 is A. And our priority in the queue is 8 because it takes a distance of 2 to get there. And we estimate that once you're at D, it's going to cost another 6. And so that gives us 8. And we've looked at all of A's children, so now we can pop the next thing off the queue, right? And that will be B. So we pop B off the Q, just like in Dijkstra's. This means we've finalized the distance to B and the best edge to E. And now we're going to look at these children. And so C goes onto the Q with priority 7. And this is because, let's take a moment and first get the distance to, right? So we realize that the cumulative distance from A to C is 4, because the distance just to get to B was 1. And then this additional edge from B to C puts us at 3 to get all the way to C, starting from A, right? And so the cumulative distance from our start to C is 4. And we estimate that from C, we're still 3 away from the goal. And so 4, the distance to, plus 3, our heuristic, is 7. And so that is all of these children. I want you to notice, really importantly, that C is on the Q with a higher priority than D and E. And so we're going to pop C off the Q next, not bothering to look at D and E. And this is partially because our heuristic is telling us, hey, don't bother going down there yet. Like, it's kind of expensive still, right? And so we're going to look at C because it's the next thing on the Q. Now from C, we look and we finalize our distance to C, and we're going to go look at our children. So first we might look at F. And just like in Dijkstra's, our distance to is cumulative. So it's going to be the distance to get to C plus this edge from C to F, which is 2. And so the distance to is 6, cumulative distance from A to F. And our edge 2 is C, because we want to traverse that edge from C to F. And our priority in the Q is 7, because the priority is the distance to F, which is 6, plus our estimated distance from F to the goal, or our heuristic, which is 1. That gives us 7. Then we are going to look at the next child of C. And so once again, we say our distance to G cumulatively would be 8, right? Because we realize, okay, our total distance to C is 4, and then it takes another 4 to get from C to G, and so that gives us 8. And it's actually not included here, but if G is our goal, our heuristic estimate from the goal to the goal should be 0, right? Like G is 0 distance away from G. And so our priority in the Q is going to be the distance to, which is 8, plus our heuristic of how long it is from G to G, which is 0. And so this gives us a priority of 8 for G in that Q, right? And now we've looked at all of these children, so we can move on to popping the next thing off the Q. We pop F off the Q, and we realize, okay, this is the best way to get to F, and we're going to look at F children now, right? Take a moment and think about if anything has to be updated here. So we see that the distance to F is 6, and then traversing this additional edge from F to G is going to cost 1, and that gives us a cumulative or total path length of 7. And so we realize the distance to G is actually 7. We have a better way to get there, and we always are looking to improve, right? So we're going to go ahead and update that and say, actually, the best way to get to G has a distance of 7, and it involves taking this edge from F to G, right? And we update G in our priority queue. So previously, maybe if we were tie breaking, D might have been on top of G in the priority queue if we were doing alphabetical tie breaking, but we've updated G to be 7, so it's going to move up in our priority queue. And now that means G is the next highest thing on the priority queue. And we've done visiting F children, so we pop G off the queue. And in A* search, you recall we are running from A to G, or a specific goal. And once we've finalized the path to that goal, we're done. We don't care about these because they're not on our path to our goal. And so this is the really awesome thing about A* I want you to notice right now, is that in Dijkstra's, to find the path from G to G, we ended up going through the whole graph, right? If we go look back at Dijkstra's, G was actually the last thing that we popped off the queue, which means that if all we were doing the whole time was looking for G, we still wasted our time looking at D and E in Dijkstra's, right? Now though, in A star, we were really efficient because our heuristic told us, hey, don't bother looking at D or E. Even if you traverse these edges, they're still pretty far away from our goal. Like, don't bother, right? And so that is the awesome thing about A star. If you have a correct heuristic, a good heuristic, it's going to tell you, don't waste your time on those nodes. They're not going to bring you any closer to your goal, or they're not going to be much closer to your goal, right? And so the heuristic is awesome. And in this case, it actually saves us a lot of time because it was admissible and consistent, and we were able to avoid paths that were not beneficial to us, or nodes that weren't on the correct path, right? And so A star can, but not always, be more efficient than Dijkstra's. And this is really awesome. So yeah, thank you for tuning in for 1B.